Oh, here we go. Oh, that's bad. How do we make that stop? Oh, right here. Hello. Can you hear? I know I'm recording, but at least... So sorry if you're watching this video. We don't want to start this over again because we've already had quite the issues trying to get this going. But anyways, so today's lesson is on geometric sequences. And let's start out by looking at number 1 and seeing if we can figure out what the next term in the sequence would be. So 2, 4, 8, and 16. And the class that I'm currently recording with is going to be answering questions. So you may or may not be able to hear some things that they say. I will try to repeat. Okay, number 1. Jada, what do you think? 32. Yes, thank you for the enthusiasm, too. You're debuting on Miss Wilson's YouTube channel today. Okay, very good. Number 2. So would this be an arithmetic sequence? Who thinks they have an idea? And if you're wrong, it's okay. Yes, it will be on here, but it's not a big deal. Just try. Would this be an arithmetic sequence? Molly?
I think so.
You think so? Right? I don't know. Is she right? Anna?
I think so because every time the numbers change, it's always increasing by the same amount. So here it's always...
It is increasing by the same amount. Jada?
I think it is because arithmetic is like division, multiplication, adding, subtracting. So that's multiplying by 2 each time.
So I get what you're saying. I'm not sure if you've done arithmetic sequences or not. The rest of my class should know what there was something special about arithmetic sequences, and down went one of the hands. Colton, I was going to call on you next.
Yes, because it has a common difference.
Does it have a common difference? What is a common difference? A common difference is when we're adding something each time. Sanji.
There is no common difference because each time the difference...
Okay, so we add 2, then we add 4, then we add 8. So it's not a common difference. We are doing something consistently. What is happening? What are you doing consistently here, Benjamin?
You're multiplying x by 2 each time.
You're multiplying by 2 each time. So, with an arithmetic sequence, we had to be adding each time. We're not adding each time. We are actually multiplying. So this is not an arithmetic sequence, okay? So you would say no. We aren't adding sorry, this is sloppy, number to the previous term. Okay, so geometric sequence, this is a geometric sequence we're going to discuss here soon. All right, let's look at number 3. So we're going to graph this, and when I say graph it, look up here. So our first term is 2, our second term is 4, our third term is 8, our fourth term is 16, and so forth, okay? So we're going to go down here and we're going to graph. So down at the bottom, we're going to put our term number, like our first term, second term, third term. So we're going to write 0, 1, 2, 3, 4. You could go further. And then over here on the side, we're going to plot what the actual term is. So I'm going to count by 2s. 2, 4, 6, 8, 10, 12, 14, 16. You could go higher than that. All right, so let's go ahead and plot this. So our first term was 2. So we go over to 1 and up to 2. Our second term was 4. So we're going to go over to 2 and up to 4. Our third term is 8. Sorry. And our fourth term is 16. What type of function does this look like? What does this look like? Simon?
A linear function.
Does it look like it would be a line? Ellen? An exponential function. Does it look like an exponential function? So look, the points are kind of curving upward. It does look like an exponential function. So come out here to the side and write looks. Don't write it is. We'll have that conversation a little bit, right? Looks like an exponential function. Okay, number 4. You know what? I'm going to skip these two for right now and come back to those if we have time. Go down here to the bottom. Geometric sequences are similar to, what goes here? Exponential functions, but geometric sequences are discrete, and exponential functions are continuous. Why can't a geometric sequence be continuous? So a geometric sequence is like this, where we have 1, 2, the first term, the second term, the third term, the fourth term, okay? And when you look at the graph here, we can't connect these dots. If we connected these dots, we would be saying that it's a continuous function. We can't connect the dots because by connecting the dots, you would be saying there are values at 1.5 and 2.5 or 3.2. You'd have values in here, and that's not possible because these numbers down here stand for the term number. We have a first term, a second term, a third term. We don't have a 1.5 term, right? Okay, so that is why this can't be continuous. It can't be continuous because you can't have and this is just for example, a 1.5 term. Or if you want to write, you can't have a 2.7th term. Okay, we just have basically our first number in the list, right? Our second number, our third number. Okay, so that's why it can't be continuous. All right, let's flip the page over and start looking here. So if you remember from arithmetic sequences, we had an explicit formula that we wrote for them. Well, we have an explicit formula here for these geometric sequences. The common ratio is what are you multiplying by each time? And if you look right here, we have to put, after we write the formula, we have to write where n equals 1. Because think about if n was 1 right here. If n was 1, 1 minus 1 would be 0. Whatever you have in here to the 0 power is now going to become 1. And then you're left with this term out here as your answer. Okay, and that's always your starting term. So by plugging in a 1 for the n, that will give us our first term in the list, because by plugging in a 1 here, that makes all of this go away. Okay, so let's go ahead and start. Number 6, a radioactive substance decreases in the amount of grams by 1/3 each year. The starting amount of the substance in a rock is 1,452 grams. What is the first term? Okay, so we're talking about a rock, and it's got radioactive material in it, okay? Initially, the rock has 1,452 grams, right? So that is the first term, okay? So 1,452. Now, we know that it is decreasing each year by 1/3, right? So that means it's the amount of radioactive material that's still in the rock after a year is 1/3 less, okay? Well, this whole situation, we have to write what is the common ratio. Like, what are we multiplying by in order to figure out how much radioactive material would still be in the rock the next year? Well, if it's going down by 1/3, what would you really be multiplying by if you're trying to figure out how much is still in the rock? Anybody? No. Colton? 2/3. Why? Because you've got 1, you're decreasing. 1 minus 1/3. 1 minus 1/3 is 2/3. Right? Yesterday with the exponential decay type of problems, right? 1 minus however much is it decreasing by? It's decreasing by 1/3. So 1 whole, or 3/3. Take away a third, leaves you with 2/3. So our common ratio is 2/3. Good. So the first 3 terms of the sequence. Well, we know the first one is 1,452. The second term is going to be 2/3 of that. So figure out, and if you're multiplying by 2/3 on your calculator, you can use your that little fraction button. Raise your hand when you've got the next amount of radioactive substance after a year. Molly? 968. If you need help plugging this into your calculator, if you need some assistance, raise your hand and Ms. Cook will come and help you. And then after another year, who can tell me how much is going to be left in the rock? Anybody different? Alan? 484. You multiplied by a third, I think. Well, did you do 968 times 2/3? 645.3. Okay, good. So 645 and a third. Very good. Thanks. Okay, now, so do you see what's happening? We've got this rock. It has this radioactive material. In a year, a third of it is lost, which means there's still 2/3 of it in there, right? And then the same thing happens in another year, okay? And so you can see the radioactive material is decreasing, correct? Okay. Part D says to write an explicit formula. So here we go. Writing the explicit formula really isn't all that bad once you've figured out the first term and you have the ratio. You're set. So you're going to write A sub n, which is A with a little n, equals your initial term, which is 1,452, times, because that's what we do in a geometric sequence here, and we are multiplying by what? 2/3 to the power of n minus 1. Remember, that's what's in the formula at the top of this page. And then you're going to write where n equals 1. Okay? Because if n equals 1, if that's our starting point, that will help us get the first term. If we plug in a 1 right here, 1 minus 1 is 0. 2/3 to the 0 power is 1. And 1,452 times 1 would just be the 1,452. That would be the initial amount. Then if you plug in 2 for your second term, that'll give you the 968. And if you plug in 3 for your third term, that'll give you the 645 and a third. Okay? All right. Let's go to number 7. Now, if you just have a list of numbers, it's almost a little bit easier here. We're supposed to be writing an explicit formula, so we're going to write A sub n equals, what's my initial term? 500 times my ratio. How are we getting from 500 to negative 400 and then from negative 400 to 320? It's got to be multiplication today because we're doing geometric sequences. If you can't figure it out, here's what you do. You take one of the numbers and you divide it by the previous number. And it doesn't matter which one in here you use. Okay, take a number and divide by the previous number. That'll give you the common ratio. Colton?
Negative 0.8.
Negative 0.8. Very good. To the power of n minus 1, where n equals 1. Meaning that's how, if we use 1, that'll give us our first term. Okay? So I know that might be a little frustrating. Why do I have to write that where n equals 1? You do. That's part of your answer. Okay? You're basically putting a limit on where to start. Okay? Starting with n equal to 1. Okay, number 8. Due to reduced taxes, Blake has an extra $600 in spendable income. Blake spends 68% of this on consumer goods. So he spends 68% of the $600 on consumer goods. Assume that the producer of these goods, okay, so basically the person that just got this money, then spends 68% of that on consumer goods, and that process continues. So you basically have Blake with $600. He spends 68% of that money, gives it to a person or a company, and then that person or company spends 68% of that money to another person or company, and then the process just continues, okay? And so we are supposed to write a formula for, or an explicit equation that's modeling what's happening here. So we're going to start out with our A sub n. What is our initial amount? 600 times, how are we getting from one number to the next? 0.68, yes. We're multiplying by 68%, 0.68. To the power of n minus 1, what do we write? Where n equals to 1. Sometimes you'll see for n equal to 1 or if n equals to 1. Basically, the n equal to 1 is just telling us where to start. With, like, if we were to create a table of values, it's basically saying start with 1 and do 1, 2, 3, 4, 5. Okay? All right, letter B says geometric sequences, okay, like a list of numbers we've had, and exponential functions are very similar. The difference is that sequences are not continuous. They are only true for discrete values. So like a list of numbers, they're discrete values. We've got our first number, our second number, our third number, our fourth number, but we're not going to have like a 1.34th number. Could one of our numbers be 1.34? Yes, but we don't actually say, okay, well, the 1.34th number is, and then give a value for that. Okay? Explain why this situation could not be modeled by an exponential function. So the situation with Blake, why is this situation, you could plot the first term, second term, and it would look exponential, okay? But why could we not connect all those points and call it an exponential function? Who has an idea? Sanji?
Because there's no answer for all of the numbers in between those dots.
Right, we don't have an answer for in between all the points. Okay, so what are the points representing?
They represent all of the terms.
The terms, and in terms of this scenario with Blake, Benjamin?
The amount of money each person spends or each company spends.
The amount would be your Y value. We're looking at more the X value. Alan?
Like how much they have to spend.
That's kind of like what Blake was saying. Anna?
How many times that they used 60%?
No. Simon?
The producers, how many producers there are? Like how many times has it been passed down?
How many times it's been passed down? I'm going to just stop all of us. But let me say, I do appreciate that you're a class that tries. And just because you're not sure, you still share, because that tells me that you're thinking. So thank you very, very much. I'm going to just go ahead and tell you the answer. Okay? So the reason that this cannot be, and maybe some of you were trying to say this but couldn't quite verbalize it. It cannot be an exponential function because it deals with the X values. If you're thinking in terms of graphing it, the X values in this scenario are referring to Blake and then the next company and the next company. It's referring to people, right? So Blake is the first person, then wherever he spent the money, that's the second person or company, if you want to call it a company. And then the third person. So it can't be an exponential function because we don't have like a 1.5 person anywhere in there, right? There's nobody between Blake and that next company. There's nothing happening in there. So that's why we can't connect it and make it an exponential function. So what you're going to write is you can't have a part, and don't try to get funny on this and say, but what if a part of a person, you can't have a part of a person slash company who is spending money on goods. Okay, you either have Blake or you have the person he gave the money to. You don't have anybody in between there. That's why it cannot be exponential. Okay, we need to quickly move on to number 9. A super ball is dropped from a height of 240 centimeters and it bounces 90% of its original height. So if we were to look at this, so let's say we have this ball and it drops all the way down here and then it drops up 90%, probably about there, right? and then about 90% of that, and then about 90% of that, and it kind of looks like this, right? See what's happening? Okay. Probably shouldn't have put a little arrow there. That looks like it's going down into the ground, but that's not what I meant. Write an explicit formula that will give the height of each bounce. Okay, so A sub n equals, what's the initial height? 240. Okay, times 0.90 or 0.9. If we do that, if we take 90% of 240, that'll tell us the height of the next bounce, right? Okay, to the power of n minus 1, where n equals 1. There we go. You guys are getting the hang of it. Good. All right, number 10. Write an explicit formula for this sequence. A sub n. There's not really a lot to process when you just have, excuse me, a list of numbers. It's not a word problem, so it's kind of pretty simple here. What's the first term? 2. What is the common ratio, or what I'm multiplying by? -3 to the power of n minus 1, where n equals 1. I know we skipped number 4 and 5. I think I'm just going to let it be for right now and not address those.